So now, actually, I should say that we want to make sure, in some sense, that this is consistent with our old rules. Like, it used to be like we just had like one option for extracting, which is like extract all, and we'd like put all 3 qubits into there, and we'd see this one with probability, we'd see 0, 0, 0 with 81%, we'd see 0, 1, 0 with probability 1%, and so forth. And actually, in most real-life implementations of qubits and measuring devices, you don't have like a measuring device that accepts like 10 qubits or 3 qubits or multiple qubits. You usually have like a measuring device that accepts 1 qubit. So really, if you want to implement extract all, what will really happen is it'll just do extract 1 by 1 on each of the qubits, because it's like a 1 qubit measuring device. So we really ought to check a couple of things. We ought to check that if we, here we did extract C and we got some bit, we should kind of check that if you now do extract B and extract A, and thereby get 3 bits, that'll be sort of the same as the old situation where we, did extract all and we got 3 bits in one shot with these probabilities. Moreover, that we should check technically that like it doesn't matter the order you extract them in. Like if you extract A, B, C, you get the same kind of probabilistic outcome as if you extract C, B, A, or whatever. So I'll do a little of this checking, and then after a while we'll be like, okay, it's fine. Let me add a little tweak to this law here, though. This law is all fine, but we're about to want to apply this law to unnormalized states. So here, like this assumed that like the state of, let's say, A, B, and C was a normalized state. We want to be able to apply it to unnormalized states because it's not convenient otherwise. So the sum of the squares of the amplitudes is not necessarily 1, but something else. But it's just going to be the same thing. I mean, really, this will just become like the fraction of the total squared amplitude that's on basic states with C equals 0. And this was just as before. I mean, if we did extract all on like an unnormalized state, rather than getting 0, 0 with probably 0.9 squared, it would be 0.9 squared divided by the total squared amplitude. And that just follows because like what you should really do is first figure out this total squared amplitude and divide by the square root of it to make a normalized state. But then when you square this, you'll indeed get 0.9 squared up here and the total squared amplitude down here. Okay. So keep this in the back of our minds. And I'm just going to continue this example, but now I'll do extract, I don't know, A. I'll be doing them in a funny order, C and then A, and then maybe we'll do B. Or maybe we'll get the gist of it. And so I'll say, and now we'll do extract A. Okay. So now you actually have to pay attention. You have to like decide which of these actually happen, because like there's really 2 cases. There's like case 0, this happened, and now this is the state of A, and now we think about of A and B, and now we think about extracting A. Or this was the case, now this is the new state of A and B, and now we think about extracting A here. So let's assume, just so we have to do all the analysis, that this was the case. Let's extract C, and suppose we got, C equals 0 was the outcome. Okay, so now this is the state, or the front face is like the new state. So we're kind of imagining that we did the extract C, it happened to output 0, and so now like the new state is like the front face here, well, with the last qubit label deleted, or this poorly drawn picture. 0, 0, 1, 0, 1, 0, whoops, 0, 1, 1, 1. Okay. So again, now in this picture, there's 2 possibilities, like it displays A equals 0 or A equals 1. And A equals 0 is like the top row, right? Again, ignoring the 3rd qubit and just looking at the front face. A equals 0 corresponds to the top row, and A equals 1 corresponds to the bottom row. And so, when the measuring device has to decide on, well, it doesn't decide, but when nature decides on whether it's going to tell you A equals 0 or A equals 1, it's kind of considering, this case or this case. So in this case, the probability, again, I'll do them in the opposite order. The outcome is like A equals 1. That's like the bottom row. So this would be like the bottom row. I should really be pointing out this picture. The bottom row fraction of squared amplitude. Okay, and that's 0.1 squared plus 0 squared over the total squared amplitude, which is 0.83. So it's 0.1 squared plus 0.0 squared over 0.83, which I'll just say is 0.01 over 0.83. Okay, it's 1/83rd, if you will. And if this happens, well, the only qubit left is B, and so we need the new state of B. So that's a new 1 qubit state, and so in these little cubical pictures, that's just like an edge, and which edge is it? It's the bottom edge. It's this one. So it's the new state of B is 0.10 plus, well, nothing. So I won't write it. And again, this is unnormalized state. Okay. What about outcome A equals 1? So let's A equals 0. So let's rewind. Let's assume that we did extract C. The outcome was 0. And now we're going to do extract A. And let's think about the probability that we get a 0 instead. On the other hand, the probability that the outcome for A is 0. This is like the fraction of squared amplitude in the top row. The top row of that little diagram, or like this diagram up here. So it's 0.9 squared. This is again all over 0.83 plus negative 0.1 squared, which is 0.82 over 0.83. And it kind of had to be this, right? Because it has to be like 1 minus this. And if this occurs, let's say, the new unnormalized state for the only qubit that's left, which is B, is 0.90 minus 0.11. Okay. This state, by the way, we would normally just call it ket 0, but it's the same thing if you have some unnormalized version with amplitude here. Okay, so now that we did these two calculations, let's ask ourselves one more question, which is, I'll erase this. If we rewind all the way to the beginning and we're say like, okay, we start with this qubit state, and now we're going to do extract C and we're going to do extract A, what happens? So we start at the beginning. If we do, extract C and then extract A, what's going to happen? What's the probability that we see, well, A equals 0 and C equals 0? Well, it's all up here on the board. There's a point. What's the chance that you see them both to be 0? There's a 0.83 chance that C equals 0. And then condition on that, luckily we did the conditioning on that. Condition on that, there's a this much chance that you see A equals 0 as well. So this is 0.83 0.83 times 0.82 over 0.83, which is 0.82. And this is also the probability of getting to here. This is the probability. Well, I should say, and with this probability, the new state of B, it's like this horizontal edge. It's the one that corresponds to A equals 0 and C equals 0. So that's 0.90 minus 0.11. That's the new unnormalized state. And you can also see directly, like this 0.82, it's like the total squared amplitude of this edge. So kind of like this is sort of checking, if you have A, B, and C, you could sort of blindly put A and C into like a measuring device and expect 2 bits back, and then ask, what's the chance you'll see A equals 0, C equals 0? It's kind of like, what's the chance that like this edge will get selected? And this is exactly the total squared amplitude on this edge. It's like 0.81 plus 0.01. Or divided by the total squared amplitude in this picture, but I started with total squared amplitude 1. Okay, so this happens in general, and hopefully you could see that like the probability of the order in which you measure the qubits doesn't matter. So let's in fact check that. So the order of measuring or extracting doesn't matter. In fact, as we'll see later in this lecture, there's like a general principle that if you do any kind of operation on like one qubit and then an operation on another qubit, as long as these operations don't involve both of them simultaneously, you should be able to do them in either order and get the same result. And we already saw this in the case where these operations are like unitaries, qubit manipulation operations. And so here I'm just checking for you, it's also true for this special operations, the extraction operations. So let's imagine we measured them in the reverse order. So let's say we did extract A first, and then we did extract C later. And asked ourselves, if we do them in this order, what's the chance that we'll get A to be 0 and C to be 0? Well, first we have to extract A first. So like the probability that like A gets measured and displayed as 0. Okay, this is the total squared amplitude of some face in this 3D diagram. So I'll ask you to see if you're following along. Which face? What does this mean? Nope, that's the C equals 0 face. But now we're measuring A. It's 1 in 5 chance now. Yeah, there's 6 faces. It's like exactly, yeah. Oh, that reminds me. Thank you. Let's get these tickets going. Here you go. Okay, we're down to a 1 in 5 chance. Yes. Yeah, it's the top face, I think. Yeah, it's the face where I unhelpfully erased the little legend up here, but the top face is the one where like all the first qubit, the A qubit is 0. So it's the total squared amplitude of the top face, which is 0.9 squared plus 0.4 squared plus negative 0.1 squared plus 0 squared, which is 81, 16 is 97, 98. So it's 0.98, 98%. So you're very likely to get A equals 0 if you measure A at the beginning. And then let's assume that happened, conditioned on this happening. The new state of the remaining qubits, which are B and C, is, well, we just retain the part of the picture where a equals 0, which is the top face, and delete the part of the picture where a wasn't 0. So I'll draw the diagram in like sort of funny way. Looks like this. And I guess it's 0.9, 0.4, 0, minus 0.1. And this is like 0, 1. And this is like 1, 1. And this is 0, 0. And this is 1, 0. Okay, I just deleted the 0 that was at the beginning of each of the labels over there. So this is a new unnormalized state, but okay. That's fine. And now let's imagine we, do extract on C. So if we extract C now, the probability of getting, 0 on our measurement device's display is the fraction of total squared amplitude on the C equals 0 setting. The C equals 0 setting is it's this edge, right? This is where C is 0. It's this edge. So that's 0.9 squared plus minus 0.1 squared. But now it's an unnormalized state here. So we have to divide by the total squared amplitude, which, hey, we just calculated up here as 0.98. So over 0.98. So that's 0.82 over 0.98. So that's the subsequent chance that you would get C equals 0. And then look, so therefore, the probability that you get, A and C to be both 0 in this sequential process is like the chance that A is 0, which is 0.98, times the chance that C is 0 condition on that, which is 0.82 over 0.98, which is 0.82. I really hope it's the same. Yeah, it's 0.82. And I won't prove any theorems or something, but it's not a coincidence that this 0.98 just cancel this 0.98 back out, and the overall probability of getting to this this particular horizontal edge is the final state of B is 0.9 squared plus negative 0.1 squared. And indeed, if we were now to extract B and go all the way down to 3 bits, the final probability that we would see A equals 0, then C equals 0, then B equals 0 would end up being our good old friend 0.81, the square of this, because we get in this edge, we get 0.9 squared divided by the total squared amplitude here, which would be 0.81 over 0.82, and the 0.82s would cancel. Okay, probably saying that in words was not really helpful, but I hope you find it all okay. So yeah, that's all I want to say for now about this final operation we never really talked about, but we can now talk about just extracting one out of several qubits. Any questions? I might add too that it's still possible that your measurement device in physical reality is of this sort of non-destructive type, where after you measure it and it says, oh, C is 0, it doesn't kill your qubit and C is still alive. But in that case, it's always the situation that C, remains alive, but it's as though you had just remade C in the basic state that the measurement outcome was. So again, in some sense, you can imagine that it's okay to imagine that the only things you allow are these extract operations, which are kill your bits. And if you extract C and it says C equals 0 on the measurement display screen, you can feel free to create a new qubit called C and set its state to 0. And that's equivalent to doing a non-destructive measurement.